Now it's time to take a look at graphical solutions to linear programming problems when you just have two variables. So here's an example. Sometimes when you have multiple variables, not just two, if you have three or four or many more, we wind up using subscripts for x sub 1, x sub 2, etc. Remember, those are just saying first x, second x, etc. They are not exponents because we are dealing with linear programming problems. And by the way, this in fact is not only a linear programming problem, but a little later is going to be called a standard linear programming problem. If I remember right, that's because we've got positive coefficients and because the quote regular constraints we have less than or equal to, along with having non-negativity constraints. So what we're going to do is use something called the method of corners. First of all, taking a look at the quote regular constraints here, if you think of x sub 1 as just x and x sub 2 as y, you could rewrite that first one by subtracting x sub 1 and then dividing by 4. So you would have y equals negative 1/4 x plus 90 as the equation in slope-intercept form. But because 360 is divisible by 1 and 4, what I did was I found the x and y intercepts and I plotted those right there. And then I'm going to connect them. And furthermore, when we put in 0, 0, obviously the origin is not on that line. So 0, 0 is a good test point. 0 plus 4 times 0 is just going to give us 0, and that is less than or equal to 360. So I would shade towards the origin. Let me get that to show up as well. Where's it at? There we go. All right. So similarly, you could subtract 2x sub 1 and have y equals negative 2x plus 300. But 300 is divisible by 2 and by 1. And so I came up with the x and y intercepts there as well. So here they are. Sure you can see that. And then connecting. All right. So again, the origin is not on that line. So using 0, 0, 2 times 0 plus 0 is just 0. That is less than or equal to 300. So we'll be shading towards the origin again. Get that to show up. And our non-negativity constraints trapping us on either on these edges here or within the first quadrant. We also need to know where those are crossing in the method of corners. Now, obviously, the non-negativity constraints cross here at 0, 0. I used elimination. You could put that in a matrix. Taking the two quote regular constraints, I call the constraints that are not the non-negativity constraints, the regular constraints. I multiplied everything on both sides by 2. And notice here that I'm looking for where the lines are crossing, where things are exactly equal. So I'm not writing the inequality symbols here. And I add that to the second regular constraint. And I'm getting the x1s to cancel. So we've got negative 7x sub 2 equals negative 420. So x sub 2 equals 60, dividing both sides by negative 7. And if I plug in 60 into the second regular constraint, subtract 60 from both sides, that's going to give me 2x sub 1 equals 240. So x sub 1 equals 120. So in order, and since I'm thinking of x sub 1 as x and x sub 2 as y, we need to see 120 comma 60. Now, the region of common shading, we've got the light blue going this way towards the origin. We have the purple going this way towards the origin. And from our non-negativity constraints, y greater than or equal to 0 and x greater than or equal to 0, it's right here. So let me cover up the rest of that in just a moment. Just putting a polygon around. Well, let's get, we don't need to see that y-intercept anymore because that's not on the polygon, but we do need to see that and that. All right, let's see what else can I hide here. See 0, 0, need to see that. All right, we don't need to see that line though. There we go. And we also need to see point A. Although that helped us to graph a line, it is not on the polygon that's obtained by finding the region of common shading. So let me hide this for a moment, show you something on the board. That region of common shading is our feasible set S, and it is bounded. So we have a theorem that tells us that when that feasible set S is bounded, then our objective function is going to have both a maximum and a minimum value on that feasible set. And what we're asked for is to find out the maximum, right here. We're supposed to maximize that. If we were to take this objective function and solve it for y, subtract ax from both sides, and then divide everything on both sides by b. Remember that dividing by b is the same as multiplying by 1 over b. What you should be thinking of is p sliding. We want to maximize it. And so for different values of p, this is staying the same. That is the slope of what I seem to recall one author calling the isoprofit lines. That's plural. because we're thinking of P sliding until we get the maximum value. So let's see that in action. Now I've chosen these values for my slider, my maximum and minimum, because I've already worked out the problem and I know it's somewhere in between where we're going to get the maximum. Notice down here, when P is negative 300, that it's not on the feasible region. We need to find something where it's crossing the feasible region and where it's the largest. So it's getting bigger up here. Oops, off the feasible region. Somewhere around there. In fact, it would seem that it is getting to the point where the last moment that it's on the feasible region is that at the point F, that was the intersection of our two regular constraints. Let's check that with the method of corners. Actually, I can bring that back up. So we have the 0, 0. We've got the point D, that was not point D, point C. 150, 0. The intersection of the non-negativity constraints, that was at 120, 60. Point B, that's 0, 90. And we're back to 0, 0. So if we look at what happens when we plug in the 4 corner points of our feasible region, plugging that into Z, remember that Z was 10x sub 1 plus 15x sub 2. So 10x sub 1 plus 15x sub 2. Plugging in these values for x sub 1 and x sub 2. The largest we ever get after doing that arithmetic is the 2100 at the point 120, 60. So that is what's producing our maximum, 120, 60, with a maximum value for Z of 2100.